Gas Hydrate Simulator Demonstration. HyperSim consists of several simulators. In this demonstration, we'll focus on the Hydrate-Free Simulator. The gas hydrate problem in deepwater drilling refers to the challenges and risks associated with the dissociation of gas hydrates in deepwater environments. Gas hydrates are crystalline solids composed of water molecules that form a lattice structure, trapping gas molecules, typically hydrocarbon C1 to C7, under high pressure and low temperature conditions. Mitigation strategies. To address the gas hydrate problem, deepwater drilling operations employ several strategies. 1. Chemical inhibitors. Increasing brine phase salinity to reduce water activity and adding methanol, glycol, or other kinetic hydrate inhibitors to drilling fluids to lower the hydrate formation temperature. 2. Pressure management. Carefully controlling hydrostatic pressure at mudline to avoid conditions that favor hydrate formation or dissociation. Additionally, real-time monitoring using advanced sensors can be implemented to detect early signs of hydrate formation or gas influx. Overall, the gas hydrate problem is a significant challenge in deepwater drilling, requiring careful planning, advanced technology, and proactive management to ensure safe and efficient operations. Failure to address these issues can lead to costly downtime. Hydrate-Free Simulator Overview. Hydrate-Free is a user-friendly, single dashboard simulator that enables users to input all necessary data, such as expected seabed temperature, maximum pressure at the mudline, expected gas composition, and KHI concentration on a single page. To further simplify the process of entering salt-related data, users can utilize Crystal Amaze to select the desired brine composition and seamlessly transfer it into the Hydrate-Free Simulator. In this demonstration, let's assume a seabed depth of 1,000 meters, 3,281 feet, and a planned mud density of 13.5 ppg, 1.62 sg. Based on these parameters, the hydrostatic pressure at the mudline is calculated as follows: 13.5 ppg times 3,281 feet times 0.052 equals to 2,303 psi. However, factors such as cuttings concentration and the increase in mud density due to compaction as temperature decreases in the riser can elevate the hydrostatic pressure at the mudline. Therefore, for this demonstration, the mudline pressure is considered to be 2,400 psi. The seabed temperature is assumed to be 40 degrees Fahrenheit, 4 degrees Celsius. Hydrate safety margin. The hydrate safety margin is set at 5 degrees Fahrenheit in this demonstration, meaning we aim to avoid gas hydrate issues even at temperatures as low as 35 degrees Fahrenheit. Water activity and brine selection. Reducing the water activity of the brine in the drilling fluid suppresses the challenges of managing gas hydrate issues. Referring to salt tables, the lowest cost brine with a density of 10 ppg is sodium chloride, which delivers a water activity of 0.763. Other brines, such as sodium bromide, sodium formate, potassium formate, and sodium nitrate, have similar or higher water activity at 10 ppg, except for potassium acetate, which delivers a water activity of 0.73. To reduce water activity below 0.763, the brine density must be increased beyond 10 ppg, which can be more costly compared to incorporating KHI like ethylene glycol into the drilling fluid. For this demonstration, we will use sodium chloride brine at 10 ppg as the base fluid for drilling mud preparation. Later, we will simulate using a higher density brine to achieve lower water activity without requiring glycol as a kinetic hydrate inhibitor. Simulation setup. 1. Go to Crystal Amaze and select a 10 ppg sodium chloride brine. 2. Run the simulation. The brine formulation consists of 311.574 pounds per barrel water and 109 pounds per barrel sodium chloride. resulting in a density of 10 ppg and a TCT of 25 degrees Fahrenheit. 3. Transfer the salt data into the hydrate-free simulator by clicking the designated button. Gas composition. The gas composition in this demo is set to default, but users can input specific gas compositions if available. Simulation execution. There are two determine gas hydrate buttons. The top button runs the simulation without incorporating KHI. The bottom button runs the simulation with added KHI. Click the determine gas hydrate button. The simulation shows that gas hydrate formation is a risk at 46.31 degrees Fahrenheit under the given mudline pressure of 2,400 psi. It's important to note that gas hydrate formation risk increases at higher temperatures as mudline pressure increases. Since the determined gas hydrate temperature at 46.31 degrees Fahrenheit is above the desired temperature, 35 degrees Fahrenheit, the results are displayed in red font. Incorporating glycol as KHI. To mitigate the gas hydrate issue, let's incorporate ethylene glycol and determine the optimal concentration. Add a new row and select ethylene glycol at 5% by volume. Run the simulation. The gas hydrate temperature reduces from 46.31 degrees Fahrenheit to 39.23 degrees Fahrenheit. Let's increase ethylene glycol from 5% to 7% by volume. Run the simulation. The gas hydrate temperature reduces to 36.16 degrees Fahrenheit. Increase the KHI concentration to 8% by volume and run the simulation. The gas hydrate temperature further reduces to 34.57 degrees Fahrenheit, which is below the desired temperature of 35 degrees Fahrenheit. Graphical analysis. 3 graphs are displayed at the bottom. 1. Gas hydrate temperature versus brine water activity. 2. Gas hydrate temperature versus mudline pressure. 3. Gas hydrate temperature versus KHI percentage by weight. Graph analysis. Let's move the cursor over to graph number 2 to analyze the relationship between pressure and gas hydrate formation temperature. The y-axis represents the gas hydrate formation temperature, while the x-axis represents the mudline pressure. As indicated by the x and y values displayed at the top of the graph, the gas hydrate formation temperature falls below 35 degrees Fahrenheit when the mudline pressure is reduced below 900 psi. Additionally, note that the red bullet, which moves with the cursor, changes to green when the pressure and temperature values fall within the free zone of gas hydrate formation. This suggests that using a seabed pump to reduce the fluid column at the mudline could mitigate gas hydrate formation. For example, maintaining a mud column height to 375 meters, calculated as 1,000 meters times 900 psi divided by 2,400 psi, in the riser would prevent gas hydrate formation. Instructions for simulation adjustment. Remove the KHI concentration and set the mudline pressure to 900 psi, which corresponds to a 375 meter hydrostatic column of 13.5 ppg drilling fluid in the riser. Run the simulation. As the results indicate, the risk of gas hydrate formation falls below 35 degrees Fahrenheit, which confirms that the conditions are within the free zone of gas hydrate formation. Alternative brine solution. Gas hydrate formation versus brine water activity analysis. Let's reset back mudline pressure to 2,400 psi and click on the Determine Gas Hydrate button. Okay, move the cursor over to graph number 1 to analyze the relationship between brine water activity and gas hydrate formation temperature. The y-axis represents the gas hydrate formation temperature, while the x-axis represents the brine water activity. As indicated by the x and y values displayed at the top of the graph, the gas hydrate formation temperature falls below 35 degrees Fahrenheit when the brine water activity is reduced to about 0.66, Additionally, note that the red bullet, which moves with the cursor, changes to green when the water activity and temperature values fall within the free zone of gas hydrate formation. Let's evaluate the use of sodium bromide without adding KHI as an alternative to sodium chloride and KHI. Navigate to Salt Rock and examine sodium bromide. At a density of approximately 1.44 Sg, 12 ppg, and a concentration of about 41% by weight, sodium bromide exhibits a water activity of approximately 0.66. This water activity is at the required threshold, as determined from the first graph, ensuring the conditions are free of gas hydrate formation. In Crystal Amaze, select sodium bromide and set the required brine density to 12 ppg. Run the simulation. Transfer the brine data into HYDRATE-FREE. Click the Determine Gas Hydrate button. The results indicate that sodium bromide at approximately 12 ppg, 41% by weight, can effectively mitigate the gas hydrate problem under the given conditions without the need for adding any KHI. Cost-benefit analysis. Finally, it's essential to evaluate whether using sodium chloride at 10 ppg with 8% by volume of ethylene glycol is more economical than switching to sodium bromide at about 12 ppg. However, it's worth noting that a 12 ppg sodium bromide base fluid offers better mud properties, such as lower plastic viscosity and improved rheology, leading to reduced equivalent circulating density, ECD, and enhanced drilling performance. I hope this demonstration has provided you with a comprehensive understanding of the Hydrate-Free Simulator and its capabilities. Thank you for your time and attention. We greatly appreciate your interest.